So let's continue where we stopped yesterday. So yesterday was on a very strange phenomenon. The first lecture I covered half of what I wanted to do in the first lecture, and in the second I covered more than I was initially planning to do. So somehow more than 50% more than I was planning in the second lecture, which probably proves that I wasn't organized very well. I heard that I didn't estimate it well, but maybe also they were a bit fast. So let's just do a slow sort of recap. So we were, thank you. So we said that we want to study kind of nonembeddability, and how we're going to do it. We're going to build invariants, which have the forms of functional inequalities. Okay? And the main invariants in the linear theory are type and cotype, either Rademacher or Markov. So Rademacher, type, and cotype are these two inequalities here. This is one inequality, this is another inequality. So you bound the pth moment of Rademacher's sum, but of course the p here is a dummy variable because of Kahan's inequality. So what matters is that the p is here. Okay, so the LP norm matters. So we bound the pth moment of Rademacher's sum either by the LP sum of the individual norms from above, or the L2 sum from below, and here p has to be smaller than 2, q has to be greater than 2. Okay, let's say a few things slowly. P equals 1 is trivial, said that. Q equals infinity is trivial. So the equivalent points are trivial. Okay. Because the variable here doesn't matter, P, the type becomes better as you approach 2. 2 is the best possible type you can have. And cotype becomes better as you approach 2. Okay, so it's a monotone property. Okay. And we also had the martingale versions of those. Okay, so where you replace your Rademacher sum by martingale, and on the other side you have the increments of the martingale.
So your martingales were using bits, but is it equivalent?
Yes, it's all equivalent. So all these properties are equivalent for general martingales and Perry-Washers. And yeah. And then we said, okay, there are some classical inequalities, well, just integral functions that allow us to prove using the vectorization argument of PZA the martingale type of LP spaces. Okay, so we know the smoothness of LP spaces because of Clarkson. We do this iteration argument that we actually proved, and you get the martingale type, at least for these very special martingales. And then we saw this argument of Alexandros allowing us to pass for martingale type, which is a linear property. I mean, it's a property of norms because I cannot define what a martingale is on a Banach space. I don't know what the midpoint of, on a metric space, because I don't know what the midpoint of 2 points is. So this is a linear property, martingale type, but we're able to use it quite easily actually, and get a nonlinear property, which is n-flu type via this argument of Christopher. Okay. And then I didn't write it, but I just mentioned it. That the moment you have n-flu type R, you immediately have a lower bound for the distortion of the hypercube, which is n to the 1 minus 1 over R. Okay, so if you plug in what R is, if P is between 1 and 2, you're going to get a distortion lower bound, which is n to the 1 minus 1 over P. If P is greater than 2, you're going to get a square root of n, but it has to be divided by square root of P, because that's the constant here. Okay, and why did we embark on this journey? Why did we think that even looking at I should have said that again yesterday, it's easy. Why did we think that some nonlinear notion of type is going to be a good invariant to embeddings of the hypercube? Because L1, if you take here your norm to be the L1 norm, and the VI's to be the basis vectors, then this side is n, and this side, it's the L1 norm of a vector of plus minus 1s. So when you raise to the power p, you have n to the p. Okay, so L1 does not have type greater than 1. This is included here also. And therefore, if I want to think of nonembeddability of the hypercube, it makes sense to look at some kind of notion, some nonlinear notion of type. Now we get this bound here, and R in general was the martingale type. But I mentioned yesterday that because of this theorem of Sasha and Roman van Handel and Pateman, really, we can also take R here to be the Rademacher type of the space. Okay? And in fact, the Rademacher type is exactly the correct parameter that you can put here. So, sorry, mark the 2 that the effects is infinite dimensional, I already mentioned a bit yesterday, the story, if you look at finite dimensional targets, is different because of this topological or circulum, the reasons that they mentioned and others. And you consider Tx to be the supremo P such that X as Rademacher P. Okay, so you take the best possible, which might or might not be attained. It's not true that it's always attained. So it could be that the constant, the type constant blows up. Then, if you look at the distortion into X of -1,1 to the n with the Hamming metric, then this can be bounded above by n to the 1 minus 1 over this optimal type constant. But it can also be bounded below by the same thing plus limit of those. Okay, so this lower bound we already, we didn't prove, but it follows from the theorem of Friedman, Handel, and Goldberg. Why? Because you take here px minus epsilon, you have Rademacher type px minus epsilon. So you run this argument, and what you get is plus epsilon, minus epsilon here for every epsilon. Okay. So some people don't like this, but yeah. So this is the only mathematical disagreement I ever had with about plus or minus. Okay. So this part we already proved. This part is a consequence of the Morin-Bézier theorem. So the deep theorem of Morin-Bézier, probably the deepest theorem in the classical theory of type and cotype, tells you that if you take this px, this parameter px, then in fact LPX, so the LP space with this parameter p, is finitely representable in your space, provided that the space is infinite dimension. So the moment the space is infinite dimension, you can actually find an LP inside with the value of p, and then this gives you this upper bound because you can always embed it to this LP and then embed it.
Presumably just the domain has to be large enough. It have to be.
Yeah, it cannot be quantified, but in very ineffective ways. Even though this is a 40-year theorem, we don't know at all the correct dependence of the dimension. Actually, that's not entirely true. So for type, we know it somewhat better, but for cotype, it's really bad. So there's a dual switch. But again, for type, it's really also not tight. Okay, that's a final remark that I want to make. So this bound here, I mean, doesn't only follow from type, but also recovers the type if you know it for every n. Okay, so you take the log of that, you divide by log n, you look at the constant you get. This is going to be 1 minus 1 over the supreme of type. Okay. Any questions about that? Okay. And then in the last part of the talk, yesterday there was a discussion of this notion of metric spaces with finite length, where I didn't prove anything. I just mentioned that basically all these Martingale arguments work very well. You have a partition that has a certain nice properties, and then you can get distortion bounds in that setting too. In a way, the partition that was used in Christoph's theorem is the one you would expect for the hypercube. You know, you condition on coordinates, but you can do the same with symmetric group, and you can do the same on body spaces. But this I won't get. It's another implementation of very similar Martingale. Okay. So I think those are 4. Yeah. So if that's okay with everyone, there are no questions. Let's move on. So this is all about type. So switch to context. And type was what was needed to study distortion of L1. Why? Because L1 doesn't have this property. What's a space that doesn't have this property? Infinity, right? So if you take this to be the vectors in infinity, this is order 1, whereas this is order n. So how should? And the discrete version of L infinity, and we're gonna explain this in a bit, is gonna be L infinity grid. So for today, we're gonna discuss L infinity grids. So, in principle, what we want is to come up with a nonlinear notion of cotype, looking a bit like M-type, okay, that we can define for functions with values in an arbitrary metric space, and then prove that if I can compute, you know, the Rademacher cotype ideally, or maybe the Martingale cotype if I'm a bit less ambitious, then I can compute this nonlinear notion of cotype and then get this notion about from that. Like we'll try to implement exactly the same program. So what would you want to do? So what did Enflo do? That's not the historical order of things, but how did we go from, if you say, from Rademacher to Enflo, you replace the Rademacher sum by a general function on the Boolean cube, and you say, well, I want, on the one side, I have differences over antipodals. The antipodals there are not really needed. It's the way he defined it. I mean, it can be differences over two independent variables if you want. That's a bit more canonical. But so on the one side, you can say I have difference over two independent variables, or antipodals, whatever you want. On the other side, I just have differences over edges. Okay, so you can say, okay, I'll just play the same game on the hypercube, just reverse some of the inequalities and see what happens. And of course, this doesn't make any sense. Why? Because on the one hand, you're going to have the variance, and now you're going to want to bump from below by the gradient. So you cannot, I mean, you can perfectly well reverse the Poincare inequality if your function is linear, but you cannot reverse the Poincare inequality if your function is anything. Right? So this simply cannot happen. So let me write and that was actually an obstacle for even the definition of metric cotype, which was a big breakthrough when it happened. There were some things proposed earlier that were more, anyway, so I won't get into the previous definitions, but basically there's only one now that captures the correct thing, and this was due to Mendel. Over. Wait. So a metric space has metric cotype Q. The number between 0 and infinity. Same for type, by the way. You know, you don't have the constraint to be bigger than 2, smaller than 2 anymore, because you're not forced to contain a line. So imagine metric space. And in fact, we have examples. If there exists, as always, a universal function, such that for every n, now the formulation of type was that for every n, every function satisfies something, okay? So here there is an additional potential quantifier. So for every n, there exists, is it visible? There exists what we call a scaling parameter, n, which is a number depending on n and the metric space, such that an inequality is satisfied for functions not on the discrete cube, but on discrete tori. Okay, so that any function f on z mod 2n to the power n into m satisfies a certain inequality. And the inequality is that I'm going to have on the left hand side now, so the partial derivatives. So it's going to be a sum as I goes from 1 to n expectation over x of vn f of x plus n line f of x. Q. So I write it first and then I'll explain. It's bounded above by c to the q m to the q, and here there is going to be an expectation over x and epsilon of the distance between f of x plus epsilon and f of x q, where x is uniform in the torus and epsilon is uniform. This one wants to be, and I'll explain what's on it.
Is there any reason we don't look at the continuous tori?
we can look at the continuous story. But the philosophy, I mean, is that you want to get the distortion of discrete spaces. Actually, for continuous story, this is where it's coming from. Maybe you can say well about this. If you look at the analog of this on the continuous stories, actually it's an easy theorem to prove that it's equivalent to Rademacher cotype. Okay? So it's all about passing from continuous to discrete. I mean, same if you just wanted to study type in the M-flow sense, say, and instead of looking at Rademacher variables, look at Gaussian variables. This was already done by PCA in the 80s, so it's known that there's a linear to nonlinear equivalence for type to a Gaussian version of M-flow type. Okay, so this is something which they understood very well, but there were a lot of extra complications in the Rademacher case. And then, here we would just get the distortion of Rn with the one method, which we knew how to compute anyway. There are various what they call differentiation theorems that tell you that even if you want the nonlinear bi-Lipschitz distortion, if you're looking between linear spaces, and the spaces are sort of reasonable, then it's always attained by a linear operator. So it would just remove the nonlinearity. Okay, so this is the definition of cotype, so let's just stare at it for a minute. And
so exists M. It's not the same thing as for every M or something?
Absolutely not. And we're going to see that. Okay, so let me get to that. Okay, so let's just try to do M equals 1. Okay? So we have a function on Z mod 2 to the N. So that's the discrete cube. Here you have, so X is uniform on the cube, and you add to it a uniform 0, 1 in this setting. So this is really the variance. Okay. Here, these are the partial derivatives. So this is really reversing the Conver inequality. Even if you put exponent 2, you cannot do it. Okay. And we're going to see that M is actually forced to be large. So what's happening is that we're looking at differences which are of two sorts. Here, we are looking at the N, so we fix our X, and we're looking at the average distance at the N infinity ball around X of radius 1. And here, we are looking at one-dimensional differences, but as we have on the ith direction a large circle of length 2m, we are really jumping to the antipodal point over there. Okay. And since we scale this difference by m, we are forced to have a factor of m to the q here, because if your function was, say, linear, I mean, the x would cancel and you're going to have a factor of m to the q. Of course, you cannot define exactly a linear function because z mod m is periodic, but more or less. Okay. So the idea at the level of definitions here is adding this scaling parameter. Okay. And let me already tell you the theorem. And I should say that, as such, we're going to see it also in the proofs, it's extremely important, and for some applications, it's actually the more important thing. What is M? How does M depend on N? Okay, so this is actually the whole problem. So the theorem, which, as is due to Mendel, and our in 2011, is that Rademacher cotype Q implies metric cotype Q. So far, this statement had been proven in the original paper also. Okay, no, I didn't say something. First of all, metric cotype implies Rademacher cotype. Okay, so when you restrict again to linear functions, what you recover is exactly Rademacher cotype. Okay, so from metric to linear is easy in this setting. Okay, slightly more difficult than an M-flow, but really also easy. Okay, so from metric to linear is the easy direction here, as it was in the case of type. Now the question is, can we do the opposite? And this was already done in the original paper of Mendel and Auer, but the best result we know is from this paper from 2011, is that Rademacher implied metric with n of the order of n to the 1 plus 1 of it. Okay, so the game here, as Yuval observed or asked, is that in principle I can always take m to be infinity. So I want to take my m as small as possible. Okay, so the smaller the m, the better the embedding applications, and we're going to get to that. So the best thing we know now is that if I have linear cotype, I get nonlinear cotype with m growing as this power of n. Okay. And that's not a theorem that we are going to get to now, but maybe I should have started with that. So let me start with an observation then. If the cardinality of M as a metric space is at least 2, and M as metric cotype Q, then this parameter, this scaling parameter M, is at least of the order of n to the 1 over 2. Okay, so I should have started with that. Okay, the order is a bit strange. So first of all, metric cotype implies linear cotype. And then we ask ourselves, does linear cotype imply metric cotype? Here's an observation which says that if it did, m could not be very small, and this is the best upper bound that we have. Okay, we did everything the wrong way, but you understand. Okay.
Alexandros, but for linear functions, these two things are clear. I mean,
with Markov. Yes, but the problem, if you want, and that's only nominally a problem, it can be resolved very easily, is that you want a function which is defined on Z mod 2m. It has to be defined on the integers mod m.
Okay.
So a linear function is not exactly defined, but the moment you write a linear function on the basis of this space, you're going to see that what you get is equivalent to Markov. You need to work through that. But somehow you need to, in the heart of it, there is something interesting, but it just goes under the rug, that these characters of this group are actually unconditional. So that there is some unconditionality to it. But this really, it's a simple observation. You take a linear function, but linear means first order in the characters of this group, and then you see that you recover linear cotype.
So if this holds for some m, will it also hold for larger m?
I think so, at least for multiples of m. Yeah, you can do things like that. And there's a lot of different versions. You can do this averaging over epsilon, which we do -1. You can take it to be -101. You can take finite alpha. So the moment you know it for every f, you have various reformulations that you can play with. But yes, I think this is true. So the bigger the m, okay. So let me prove this observation for you. Let me prove that m has to be large. Okay. It's a very easy proof in a way. So choose a random function. Okay, sorry. So just say but take two different points in my metric space and choose a random function f from z mod 2m into m such that each f of x is either a with probability a half or b with probability a half. Okay, and that's independently over x. Okay, so for each x, you flip a coin, you say either good B or good B. And suppose that this inequality holds. Okay, so let me just give the name star. So if this inequality holds, let's just see what's the expectation over f over this random function. Okay, so this holds for every random function f. So let's just see what the expectation over f of the left-hand side of star. I'm going to swap all the sums and expectations. Okay, and I'll have the expectation over f of this quantity here. Okay. But these are, so x and x plus mei are two different points on the hypercube. So with probability a half, f of them is the same, with probability a half, f of them is different. So the expectation over f of this distance is a half times the distance from a to b to the cube. So this is, there's a n here, so n over 2 is distance q. And if I do the same for the right hand side, I again put it inside. These are two different points. Again, this is going to be a half times the distance from A to B to the q. Right. So what we're going to have is c to the q, n to the q over 2, and the distance over the q. And this implies, since this is smaller than that m is greater than n to the 1 over q over this constant. Okay, so the moment your metric space is not entirely trivial, this parameter cannot be small. In practice, what very often happens is that you're going to see in the theorem that I'm going to prove today, that rather than m to the q here, what we have is m to the q plus n. Okay, so you have both m to the q and the dimension. And then, I mean, there's no restriction. This could in principle hold. Maybe that would have also been a good formulation for the definition, but okay. So there's this notion of cotype, metric cotype. It coincides with the linear notion of cotype, and we do not know. So this is the, if you want, the major open question on this field, which is, does Rademacher cotype imply what we call sharp. So sharp metric cotype always means taking m to be of the correct integer. Okay, and I'll explain a bit later some geometric applications for which, even if you have m to be n to the 1 over q times log, the application breaks down. So there are instances where this has to be absolutely sharp, no low terms, no nothing. Okay, so there's geometric reasons for which we really care about having this. And the theorem which I would prove next, it's from a paper in our
this open question, doesn't the theorem of Giladin, Mendel, say the same thing?
No, there's the exponent here.
Oh, there's one, yes.
Yeah, so we really want the sharp exponent. Yeah. Okay. So it's really about the exponent now. So the theorem which we proved is that martingale type, okay, Q implies sharp metric cotype. Okay, so we're going to see that under martingale conditions, the problem can be
Alexandros, do you think it's really exactly correct definition of metric cotype?
Given the applications, yes. Modulo equivalent reformulations, perhaps. but it's something which really has it has been useful throughout and in places that we wouldn't expect. I'm not sure if I get to that, but it's a kind of invariant that we've used way outside Banach space. In the geometry of Wasser state spaces, we've done things using it in Alexandros geometry, so maybe I'll say a word about that. So it's something which, I mean, it's meant to be something that's coming from Banach space, and it's for Banach space, but actually it has been useful very much outside Banach space theory. So I know it's a good definition from that point of view. Maybe there's a different one, which is still equivalent to Rademacher cotype for norms, and one can prove things with it too. But it's definitely one that has been very influential. Now this theorem, the way I attributed it, the credit is a bit fake in the sense that this implication followed also from previous work. So that if you have martingale cotype, then you can get the sharp metric cotype. Okay, so in fact, there's again in the original paper of Mendel, we proved that if you have Rademacher cotype and non-trivial Rademacher type, which spaces of martingale cotype Q are known to have for some reasons, then you actually have sharp metric cotype. So from the point of view of Banach space, this is not new. The novelty in that paper that we wrote is that there's a notion of martingale cotype for metric spaces, which I won't get to here, but it's satisfied by spaces of non-positive curvature. So basically what we wanted to do in that paper was evaluate the sharp metric cotype of spaces of non-positive curvature, which are nonlinear spaces. And this led at the time to, so we were motivated, this resolved the 30-year-old question of Gromov in coarse Alexandros geometry. So we needed to compute this metric cotype of this class of spaces to answer something that had nothing to do with Banach spaces. But in particular, if you restrict the argument to Banach space, it gives this implication that I wrote here, even though this was non-linear. But the argument which I'm going to show you is the argument which just works for metric spaces as well, but I'm not going to define the notions for metric spaces. Okay. So let's see. Maybe I should first mention the application, because if there are no more questions on the statement. So let me take the corollary. Corollary, just to get one idea of the necessity of the scaling. So if M has sharp metric cotype Q, then the bi-Lipschitz distortion required to embed into M the grid of length M to the power N with the infinity norm is bounded below by what? So it should be the minimum of find out in a bit, but I think it's going to be better. Okay, we actually check it out. Q on one side. Okay, so proof. So suppose that I'm going to start by making a mistake. Okay, I'm going to start by treating it, but I'm going to identify this grid with Z mod 2M. Okay, so in the space I want to compute the distortion, I mean the distance is not exactly the same as the distance on the torus, because one of the two is folded, and the other one is unfolded. Okay, but in a way the two are not so different. Like you can embed one of those into one of this if you increase the dimension a bit, or if you enlarge the width. Okay, so getting this kind of distortion bound for that or for that is equivalent. So maybe just trust me that I'm allowed to do this identification. Okay. Okay, and suppose f from z mod 2m to bn into m is bi-Lipschitz. So what I mean is that the distance in the image of f of x and f of y is bound above by capital D times this infinity norm and bounded from below by this. Okay, so for every x and y on the torus, which I identify with it. And again, I mean here it's a metric space, so I should put that scaling parameter. It's going to cancel out from left and right. Okay, so I'm not going to do that. Okay, then we have this inequality there. We have star, right? So then the left-hand side of star is bounded from below by a sum over I of the expected distance between x plus MEI and x to the cube. Okay, and this is exactly m to the cube, right? So this is m to the cube times n. And the right-hand side of star is bounded above by, I'm going to apply the upper bound, I'm going to get a c to the cube, d to the cube, m to the cube, and you see that the scaling parameter will not play a role, times the expected distance over x and epsilon of x plus epsilon minus x in infinity to the cube. But as we said, x and x plus epsilon are at an infinity distance 1, so this is just 1. Okay? So this is CDM to the cube. And what this is going to give is that d to the cube is bounded below by n to the 1 over 2, provided that m is greater than the scaling parameter. Right, so I'm only allowed to apply this inequality for m that's greater than n to the 1 over 2.
Yes, you have one to yes, d, not d to the q.
Here?
No, below.
Yeah.
Yes, thank you. Provided that m is greater than n to the 1 over 2. Okay, to be able to apply the inequality, because as we said, it's monophonous in M. Yeah. But if m is smaller than n to the 1 over 2, then the n infinity grid of length n contains the n infinity grid of length m and the dimension m to the cube. Okay, because I just forget some of the dimensions. And then I just reapply the same thing, but on this n infinity grid where I'm allowed. You reapply. Okay, so the behavior of this distortion suddenly becomes sensitive to how much I scale and to how many dimensions I have. Okay? And actually this is sharp. So if you take your metric space here to be Hilbert space, this is exactly the correct answer. So it's m, it's square root of n. So it's m as you grow, and then at some point you stabilize at square root of n, and of course you stabilize at square root of n at the point that you just have to embed the whole space by a linear operator. But if your grid is small enough, then you can do better. And I mentioned this passingly yesterday. I mean, if you take your m equals 1, and you look at the L infinity norm, all the distances are equal to 1. So this is just a simplex, which you can always embed in Hilbert space. Okay, so this is the first embedding application. Again, it falls completely in the philosophy of I have some probability measure over distances on the left, some probability measure over distance on the right. Just that these measures are becoming more and more complicated as we proceed this week. But it really falls in the Matuszek classification of bi-Lipschitz embeddability, right? It's a Poincare inequality of that form.
Sorry, maybe I missed something, but why did you need this case study into the size of m? I mean, you estimate the left-hand side from below by mq times n, and the right-hand side, there is also mq. I mean, why doesn't the mq just, m to the q just cancel out from both sides?
It cancels, but the inequality is only valid if m is greater than n to the 1 over 2, right? So the inequality, so I assumed that the space has a sharp metric cotype, which means that the inequality is valid only if that happens.
Ah, I see.
So if that doesn't happen, I simply don't have the inequality,
right?
But I just go to a subgroup. So you can always, in fact, as far as distortion bounds are assumed, are concerned, you can always assume that m is the scaling parameter of that space. So even in the case of n to the 1 plus 1 over 2, this is going to give you something different, right? If you just plug in their theorem, it's going to give you something different for this distortion. So you're going to get this for m greater than n to the 1 plus 1 over 2, and then you're going to, I don't know what it has to be, 1 over 1 plus 1 over 2 here. Okay, good. So maybe let's, before doing the other geometric application, I'll actually go ahead and prove the theorem. How much? Okay. So let me show you the proof of this theorem. Okay, that martingale cotype implies metric cotype with a scaling parameter, and we're going to see where the scaling comes in. Everything is going to become clear. Okay. Proof of this result. Okay, so maybe a bit more complicated than the other ones, but not horribly. So, and the similarity with the proof that we saw of Christopher martingale type is that we're going to use exactly the same Pelly-Walsh martingales. Okay, we have to come up with some martingales. I mean, we have a martingale assumption. So given a function h just on the hypercube into x, we consider ei of h, so an ith averaging operator acting on h. I just want to make sure my notation is what I want it to be. So this is going to be, I'm switching the notation from, so up until the last lecture I had x for the Boolean variable. Now x is for the uniform, for the torus, so Booleans are going to be epsilons, okay? So ei of h at the vector epsilon 1 up to epsilon I is what you expect it to be, so it's the expectation over the remaining variables of h at this point. Okay, and then here epsilon I is, sorry, actually 1 up to epsilon I. Okay, so this is a martingale. With values of x. Okay. Please. And for x, so I'll consider a function, this is just for simplicity, I'll consider my function to be defined on the discrete torus of length 4n rather than 2n, it doesn't matter, and it's existentially n, so I can take the multiple of 4, and x and z mod 4n. In the end, I will consider the function f sub x on the hypercube to be f sub x at the vector is f of x plus x. Okay, so you just look at the hypercube around the point x. Okay. I should definitely keep the inequality. Yeah. Okay, so the type of argument that we're going to use is something which they call in this field, let's say, a smoothing and approximation scheme. So the idea is that we're going to start with a general f. We are going to smoothen it enough, so replace it in all the estimates by some averaging operator applied to f. Okay? This averaging operator creates some kind of linearity. In principle, we would want it to be sort of a rather large sum to apply cotype, but now it's going to be a bit like a martingale. So we're going to apply the martingale, the linear condition, on this averaging operator applied to f. And then finally, what we would want to do is to say that by passing from f to that averaging operator of f, we didn't lose confusion. So this is the plan of the proof. Okay, so I'm going to start from the side. This is the inequality we want to prove, so just keep it here. So then the left-hand side is, I'll just repeat it, sum I goes from 1 to n, expectation over x. Remember, it's Z mod 4m now, so I have here f of x plus 2m pi minus f of x to the cube. What I'm going to do is that on the ith term, I'm going to sort of add and subtract this ith martingale term. Okay? But for this, I first need to do something fairly stupid, which is to say that this is the sum as I goes from 1 to n, expectation over x, and epsilon of the function f sub whatever we have here. Okay, so this is just nothing, right? So I took x and I replaced it by x plus epsilon, and I just averaged over the epsilon. So far I've done nothing. Okay. So this is translation invariance. Okay, and now what I want to do is, as I said, go here and on the ith term add and subtract the EI operator applied to this function. Okay, so this is going to be a sum as I goes from 1 to n. I'm going to apply also Hausdorff a few times. So there's going to be expectation over x and epsilon. Here I'm going to have f sub x plus 2m EI at epsilon minus EI of that thing. Then it's going to be the difference of the martingale terms. And then finally, the last word. Okay, so I'm going and I'm replacing the, what should I pay here? It should be 2 times, it should be 3 to the cube. It doesn't matter. Okay, so just adding and subtracting these intermediate martingale terms.
Yeah, but this is to the power of q. This is 3.
Yeah, anyway, constants to the q will really not matter. But it's okay. I would just be careful since this is of course. And also, the first term and the last term are the same. Okay, so the first term and the last term are the same. So I'm going to have the first, which is 2 times e to the q minus 1, sum I goes from 1 to n, and I have expectation over x and epsilon. It's ei fx at epsilon minus fx. Epsilon to the q plus 3 to the q minus 1, sum over I, expectation over x and epsilon, ei fx plus 2m ei epsilon minus ti fx. Okay. So this is where we are, and again I'm replacing f sub x by this smoothed out version of f sub x, and here I have an approximation term. Here, as you can understand, I want to say that these two are not very far apart. And here I want to say that now that I smoothen things out, I'm somehow in better shape. I can somehow see a marginal thing. Okay, so this is going to be term number 1. This is going to be term number 2. So let's deal with term number 1 first. Okay, so for term number 1, for the approximation term, I'm going to do one more step, which is that I will add and subtract f of x. So that's for a fixed. Okay, I decided to be careful with the constant, but now I changed my mind. Okay, so too much. So I'm going to add and subtract f of x. Okay. So there's a constant depending on q. Epsilon, and here I'll have ei of fx at epsilon minus f of x. The q plus fx at epsilon minus f of x. The q. Okay, so just add and subtract f of x. Why do I add and subtract f of x? Because I have in mind the right-hand side I want to end up with, right? So I want to end up with f of x plus epsilon minus f of x. Okay? And this here is really f of x plus epsilon minus f of x. So this term is great. It's what I want to have. And what this is an averaging operator, ei, applied to f of x plus epsilon minus f of x. Right? So ei is just an averaging operator on the ith variables. So by Jensen's inequality, if I just pull it out, what I'm going to end up with is again f of x plus epsilon minus f of x. Okay? So this is just a conditional expectation of this quantity here over some of the epsilon variables. Right? So this is bound above. I have a factor n, which I promised you. So it's n expectation over x and epsilon f of x plus epsilon minus f of x. So this is the approximation part, which is sort of to be expected. That if the dimension is large enough, if the dimension is small enough, then you didn't lose too much. Okay? So far we haven't really used anything, right? This I could do for any Banach space. Okay, so the question is how to bound 2. How will a martingale appear here? Okay. So fix the parameter I between 1 and n. So fix a direction I'm in, and also fix the epsilon between minus 1 and 1 to the n. And then my claim is that if you look at the expectation over x, f x sub 2m ei at epsilon minus f sub x epsilon to the q. Now I don't care anymore about the scaling, about the fact that m is large. There's something for which I sort of cared here, because I wanted n to be smaller than n to the q. But now I'm just going to completely q on the n. Okay, so I have a circle, if you want, in the ith direction. So this is z mod 2n. So z mod 4n, sorry. So here I have x. Here I have the antipodal x plus 2m ei. So this is the antipodal of the ith circle. And what I'm going to do is I'm going to go from here to here with steps of length 2. So So here I need to be a bit careful with the constants, so it's expectation over x. And here I'm going to write a sum. M goes from 1 to m, f sub x plus 2l pi, f sub x plus 2l pi epsilon minus f sub x plus 2l minus 1 pi epsilon. This is a telescopic sum, I did nothing. So I'm just going with steps of length 2 like this, and I'm going to apply the trivial triangle inequality. So I'm just going to pull out an m to the q minus 1. Okay, so the sum of L goes from 1 to n. Expectation over x for these distances, x plus 2L pi epsilon minus f sub x plus 2 minus 1 pi q. Timing. Are there any questions about this inequality? Okay. So, and now here you'll see also that the L is again a dummy variable, right? So you can replace x by x plus 2L minus 1 EI, and what you have is just the same, right? So this is equal to m to the q times expectation over x f stopping what f sub x plus 2 pi epsilon minus f sub x to the q. And so far I got my m to the q factor, which I wanted to have. Okay. But there was something slightly arbitrary in I didn't think well of this. There's something up here, which is that I wanted to go from x to x plus 2 MEI in one direction, and I think it just went this way, depending on how you feel. But it could also go the other way. Okay? So it could have a plus or it could have a minus, and I'll tell you what the right thing to have is. I wanted to write x plus 2 MEI as minus 2n epsilon I EI. Notice that the epsilon is fixed. So here there's going to be a minus. No, I'm ruining all your notes now. And then minus epsilon I. And again, a minus epsilon I here. And a minus epsilon I. So I'm just saying that I can go from one side to the other, left or right. It doesn't matter. And what I end up with is this minus 2 epsilon I. Okay. I didn't do anything deep. But why do I care? So let us compute there's an EI applied everywhere, right?
It's the same epsilon I from the fixed
Yes,
epsilon.
it's exactly the same, but sorry about that. But in 2 there's an EI. I mean, the whole point is that they've already applied the averaging operator, right? So everywhere there's an EI. EI. Now it should be correct. I want to use the fact that they smoothed out, right? So here I have EI at this and EI at that. And now it's correct. And let's just compute what this thing is. So what is EI of this quantity here? So EI f sub x minus 2 epsilon I EI epsilon is an expectation over delta I plus 1 up to delta n. I'm going to have f sub that, so I'll just write what it is. So that's f x minus 2 epsilon I EI plus the vector that's here. So it's plus the vector which is epsilon 1 up to epsilon I, and then delta I plus 1 up to delta I. So, okay, so here I'm just writing what f sub x is. So it's f at this point plus this vector which is first epsilon and then delta. And why did I choose this funny direction here? Because in the i's coordinate, this is just going to be the point at minus I. So it's the expectation over delta I plus 1 up to delta n f at x plus epsilon 1, epsilon I minus 1, minus epsilon I, delta I plus 1, delta n. Which, if I am to rewrite it again for what it was, it's EI of f sub x now at the point epsilon 1, epsilon I minus 1, but minus epsilon I. Now I draw the same picture I drew yesterday. So here is EI of fx at epsilon. And now this is EI of fx at this point here. So what's the distance between the two? Or more, what's their midpoint? Their midpoint is EI minus 1. Okay, okay, I just continue. So I wanted to bound this quantity 2. Okay, let's just do it together. This quantity 2 was bounded by m to the q times the sum over I of these things here, which is the sum over I of these things here. And we just understood that this quantity here is exactly the sum of EI minus 1, right? Up to a factor 2. Okay.
So you need another 2 to the q, not the q.
Yeah. We're already some.
Yeah, okay, yeah, right.
About the mutual word. Okay, so here, if I condition on x now, suppose that x is fixed, as a function of epsilon, these are just Martingale differences, right? So on epsilon, I can apply Martingale cotype. Okay, I write a c to the, maybe k to the 2 No, confused. This is the cotype concept. What's going to be hidden here? So it's going to be an expectation now over the section epsilon of the last term of the martingale minus the zero term of the martingale. Now the last term is just f of x plus epsilon. What's written here is the expectation over epsilon of f of x plus epsilon. So again, I'm going to add and subtract f of x to end up with f of x plus epsilon minus f, right? So this is bound over the expectation of x to f of x plus epsilon. F of x, the q, and here we're going to have an expectation over x. This E0 is just an expectation over epsilon, or f of x plus epsilon minus f of x, the q. And this is bound about by f of x plus epsilon. F of x. Okay, so, and that's it, right? So if I take, sorry, I forgot the m to the q everywhere. There's an m to the q from everything, right? So if I add up 1 plus 2, from the factor of 1, which was the approximation term, we got a factor of n. From factor 2, which was a smoothing term, we get a factor of n to the q. And it's all multiplied by the right-hand side of the cotype inequality. And that's the end. So, in a way, I mean, you use the same martingale, but so you have your function, you replace it by the smoothed out average, and then conditioning on this little point x, you apply this martingale inequality on the neighborhood of x. And then you add this up, and what you get is really this sort of increments of a global martingale. And then martingale cotype comes into play. Are there any questions? I might make one last remark. Okay, but this is a fully dual theorem of what, say, Christoph had proven that for martingale type, you can go to the metric version, and this is what's happening here. Maybe no, okay, not very sure. I'll say the next things I want next time. Yeah, okay, so that's it for today. Thank you.